All right. Well, let us continue our discussion of gases. And we're going to start looking at some of the historic people who measured gases and who studied gases. And one of them was Robert Boyle. And Robert Boyle was concerned with the relationship of pressure and volume. And if we want to graph a pressure versus volume here, as I know, if I increase the pressure on a gas, if I squish it down, the volume is going to be smaller. So I'm going to get some kind of a curve like that. And in science, a lot of times it's nice to have a straight line. So I find that these two are inversely proportional. If I can take 1 over v instead of v, I end up getting a straight line, which is a little bit easier to deal with, okay? And what he found is that the pressure times the volume of a gas is equal to a constant. Okay, as long as I kept the temperature the same and the same amount of gas, the Boyle's law is a constant. Pressure times volume is a constant, which means that if I change one condition, the other one will respond to it, or P1 V1 equals P2 V2. And I can do a really simple example here. Let's say I have 2 atmospheres of gas at a volume of 4.0 liters. What is going to be the new volume if I increase volume? Well, let's see. If I increase the pressure to 4 atmospheres. This one works out actually really simple. I picked some easy numbers here. So these two are going to be P1 and V1. This is going to be P2 here, and V2 is going to be my unknown. So let's substitute in here 2.0 atmospheres times 4.0 liters is equal to P2, which is 4.0 atmospheres times V2. Solving for V2 is equal to 2.0 liters. Again, this is a really simple problem, but you get the idea. Now, there's some things that we need to recognize. Notice that the pressure was in the same units on both sides, and the volume was in the same units, okay? So that's easy enough. So pressure times volume is equal to a constant. That's Boyle's law. Now, some other people measured gas laws too. Another was a guy by the name of Charles. And when we take a look at Charles' law, now first just a little commentary. This is how I learned to show possessive. So Charles' law looks at the relationship between volume and temperature. And he found that was different than pressure and volume. If the temperature of a gas increases, it causes the volume to go up. Think, if you heat a gas, it expands, okay? And he said that volume over temperature is equal to a constant. Now, we have to be careful here, but let's take a look, which means that V1 over T1 is equal to V2 over T2. This is another way we can say Charles' law. So let's take this. Let's say I start with a 10.0 liters of gas at 10 degrees Celsius, and I decrease temperature by 20 degrees Celsius. I'm going to have you pause the video, solve this, and see what you get. Well, when some of you put this in, you may have had a little problem here, okay? Because if I put it in there just like this, I'm going to have my volume, that's easy enough, 10.0 liters, and my temperature, 10.0 degrees Celsius, is equal to V2. And if I take 10 and decrease it by 20 degrees, that gives me negative 10 degrees Celsius. I can't have a negative volume. This would give me a negative 10 liters per volume. Well, just as I can't have a negative volume, I need a temperature scale that is absolute. So instead of using degrees Celsius, we need to use Kelvin. And remember, to go from Celsius to Kelvin, we add 273. So this would be 283 Kelvin, and this would be 263 Kelvin. And this one, again, I get my handy dandy calculator out. 10 divided by 283. And I get my volume of 9.29 liters. Okay, so again, units are important, and it's not just in the case of temperature that you have the same units, but your units need to be in Kelvin. Now, there's other gas laws that are studied. Another one is Gay-Lussac's law. And Gay-Lussac studied the relationship of pressure and temperature, kept the container the same, and the amount of gas the same. But if he heated it, he found out that pressure went up. So pressure over temperature is a constant. Or I could say P1 over T1 equals P2 over T2. Now, again, I could go ahead and calculate a problem with that, but I think we're getting the idea. You come up with an equation, identify some things, plug it in, punch a whole buttons in your calculator, do it twice because you're afraid you messed up the first time, but you get the idea. Now, these three laws are often put together in something called the combined gas law. So P1V1 over T1 equals P2V2 over T2. And again, I can make corrections and calculations with this. If you're working a problem and you find out that, oh, hey, I've got two pressures, a volume, I'm looking for another volume, and the temperature is held constant, wow, temperature is constant. Those two are going to cancel out. I can get Boyle's law from that just by knowing that the temperature is a constant. So you don't need to memorize all the laws. You just need to know this one, okay, and be able to solve it. But we're not done. There's more people that studied gases. Remember the mole? Okay, we can measure moles of a gas. And Avogadro found that if I kept the temperature and pressure the same, the volume over the number of moles is equal to a constant. And this is Avogadro's law. Now, one thing about this, okay, what's interesting about it is that there is a certain set of conditions that we call STP, standard temperature and pressure. Now, the standard temperature for a gas is a temperature that's easy to maintain. This is 0 Celsius, also known as 273 Kelvin, because if I can maintain ice water, I have my 0 degrees Celsius. That's easy to maintain. And they went with standard atmospheric pressure, that 1 atmosphere. This is STP, fairly easy to use, okay? And often we're going to do this. Now at STP, if I have 1 mole of a gas, it's going to occupy 22.4 liters. And I think I will leave you to prove that on your own. Okay. Now, interesting here. I have a constant. All right. I have a constant here. 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 Now, what do we get if we multiply two constants by each other? Right, another constant. What happens if we divide two constants? Right, another constant. Well, I'm going to combine all of these constants together. And I'm going to look, and we're going to put pressure and volume on one side. And we're going to put moles and temperature on the other. And I'm going to put my constant here. And I'm going to give my constant a name. We're going to call it the ideal gas constant. And the value of that, the unknown for that is going to be R. So R is the ideal gas constant. And it is in SI units, 8.314 joules per mole K. Now, another useful way of writing this is 8.314 liter kilopascals per mole Kelvin. I will leave you to prove that a joule and a liter kilopascal are the same thing. But another set of units that we'll often use is 0.08206 liter atmospheres per mole Kelvin. And with this, I can solve the ideal gas equation. As long as I have 3 out of the 4 My four variables are pressure, volume, moles, and temperature. If I have 3 out of the 4, I can solve for any one of those. And I'm going to leave those for problems for you to work. Now, we're going to look at a couple other things with the ideal gas equation that we can also do. Okay? And what's interesting is that there are other ways that I can express moles. Remember, we learned that moles are equal to mass over molar mass. I'm going to write molar mass at the moment. Okay. And I want you to look in your book and see what symbol the book uses for molar mass. Okay, because every book uses a different one. I'm just going to write molar mass for the moment. So I can substitute, wow, N equals this, I can put this in for N, okay? And what this means is that pressure times volume is equal to mass over molar mass, RT. I can solve this for molar mass. I will leave you to do that later. Now notice I also have a mass and a volume. I can find mass over volume. I can determine the density of gas. These are some things I can solve from the ideal gas equation. So these are the important gas laws so far. We have Boyles, Charles, Gay-Lussac's, Avogadro's law. We have the combined gas law. We have the ideal gas law. We also have Dalton's law. And Dalton's law of partial pressures is the real name for it. And what it's saying is that if a gas is made of 2 components, all right, let's say I have gas A and gas B. The collisions of A molecules on the walls are going to give a certain amount of pressure. And the collision of gas B on the walls are going to have another set of pressure. And the total pressure is equal to the sum of those pressures. Etc. Now you're thinking, okay, does this have any real applications? Yes. Okay. For example, if your gases are a mixture of oxygen and something else, and you're wanting your lungs to absorb the oxygen, the pressure of oxygen in the air is going to be important. Okay. Now, another way that we can look at Dalton's law is we can use a unit called a mole fraction. And I don't mean you take a mole and chop the tail off, and here you have this tail. That's not a mole fraction I'm talking about. I am talking about mole fraction, which is given the Greek letter chi. Moles of whatever part, I'm going to call it A in this case, moles of A over total moles is going to be equal to the mole fraction of A. Okay? We can do this. All right? So what this means then is that the pressure of gas A is equal to the pressure total times the mole fraction of gas A. Okay. Now, where this is going to be important is that if we collect a gas over water, some of that water is going to evaporate. So if I decide I want to collect hydrogen gas, the hydrogen gas, I could collect it over mercury. That would be one way to do it. But I don't like working with mercury. Something about like dying from mercury poisoning or even just going mad from it. I don't like that. So we don't collect things over mercury very often. We're going to collect a gas over water. And if we collect hydrogen gas over water, that hydrogen gas, we measure the pressure of it. It's not going to be pure hydrogen gas. It is going to be hydrogen gas plus some water vapor. And the water vapor is going to be dependent on the temperature. At different temperatures, I will have different amounts of water. Okay. Now, our air that we see here has a lot of water in it. Now, if our air was saturated with water, we would say the relative humidity is 100%. So at a particular temperature, there's a certain amount of water air can hold. And if we're at that amount, the humidity is 100%. If we're at half of that amount, we say the humidity is 50%. So you see, this is where we get those terms from. All right, so Dalton's law is another one that we're going to need to look at. All right, there are other gas laws. We will look at those in other videos, but this should allow you to work a lot of the problems, a lot of the button punching problems is what I like to call them, where you're given information, you solve for one variable or another. And I'll have you look at those problems and the assignment.